Okay, so I suppose we're just going to skip the part where we solve practice questions, no? Uh, I don't really have a stylus at the moment, so I can't really teach these step by step. But yeah, I'll just show you my notes. Uh, Loschmidt constant. Okay. So here we use the ice table. So this part is something that I'm not really sure with. Uh, yeah, so we use the Graham's law of effusion in this problem. It says here escape through a pinhole, so that already tells you that effusion has occurred. So this is a summary of the three methods for molecular weight determination. Mayer's method for volatile liquids, Regnald's method for permanent gases, method of limiting densities to find the exact molar mass. And yes, here we use linear regression. An example, by the way, of a volatile substance is acetaldehyde or ethanol. And yeah, these are the formulas that you have to know. Okay, so we are now at part 2, um, lesson 2 rather. Kinetic model, molecular speeds, collision frequency, and we are going to have our first encounter with real gases. In CHE thermodynamics, real gases are the concept on real gases is expanded on. We're gonna encounter more equation of states than what we're going to encounter here. Namely, those equation of states are the ideal gas. We've already known that since high school. Uh, but here in college, we are going to have our first encounter with the van der Waals equation of state, uh, the Terrizzi equation of state, the Berthelot equation of state. There's one more. Uh, I can't exactly remember at the moment. I'm still on vacation mode technically, but we will encounter it here. Okay, so kinetic theory of gases. We have there are three statements here. So first is a gas consists of molecules of mass m that moves in ceaseless and random motion. So what this means is the kinetic energy is high. So obeying the laws of classical mechanics. Second statement, the size of the molecules is negligible, such that their diameters are much smaller compared to the average distance traveled between collisions. So this adjective, this negligible, um, more specifically, the volume of independent molecules is considered negligible. This is mentioned from the classic list. No, I think that's from the video part 1. Uh, I mentioned about uh, the statements on the kinetic theory, um, the complete list. So in comparison to their distances between each other, uh, the volume of the individual molecules is negligible. Third, the interaction between molecules are only through brief elastic collisions in which the total translational kinetic energy of the molecules is conserved. So, in other words, what's involved here is a perfectly elastic collision. It's described by kinetic energy and momentum being conserved. So P here is momentum. So in the concept of collisions, there is something called coefficient of restitution. And if it is E equals 1, then there is no kinetic energy that's lost, as in zero. Zero energy lost. Okay? And yes, this coefficient is a parameter that describes the type of elasticity. So it depends on the number. If it's 1, then there's no kinetic energy lost. So, okay, so this part is technically part of the syllabus, but from my experience, I won't be able to teach this part. Um, there are no practice questions, so yeah, we'll skip that part. Mhm. With the assumption of molecular chaos, assumption that the velocities of colliding particles are uncorrelated and independent of position, then the pressure exerted on the area of the wall is. Mm. So we have pressure now. Pressure is equal to force over area. Force, sorry, Newton meter. Hmm. We'll skip that part. I think that's derivation. This formula is going to be provided in the exam. For convenience, the molecules of a gas is assumed to move with a constant velocity. However, not all molecules move with constant velocity. As a result of collision, which then results to redistribution of both velocity and energy. So from the Maxwell Boltzmann probability distribution, um, the actual distribution of molecular velocities depend on the temperature and the molar mass of the gas. This makes sense since molecular velocities, if the temperature is higher, then uh, the kinetic energy is definitely higher. So molecular velocities, their movement is much faster. Um, Regarding the molar mass of a gas, if it's pretty high, then I think generally uh, it's more difficult to increase its temperature. I think that's the relationship, although I might be wrong. But whatever's written here is already established objectively. Okay? So, yeah. The Boltzmann constant is constant 25 in your calculator, at least for the Canon SGA 7892 or 1. 1 rather, to be sure. The probability of finding molecules with a velocity is given by this. I don't recall this being part of the exam, so we'll skip that. Yeah. But if ever, then the formula is gonna be provided anyways. Unless your professor is the type to not provide anything at all. Although I don't think that's likely. So this is the graph where you plot speed and fraction per meter second. This is, I think, momentum. Not really sure. It's been a while. We have, but essentially, we have this bell curve And at its highest point, this is where we point out the most probable speed, or v sub p. Then after that, we have the average speed, the one in the middle. So you just put a dash in the symbol, no? Dash v. Then we have root mean square speed, VRMS. Remember these symbols because they're gonna be important later on. This is the part where you have to memorize. So, regarding the effect of temperature, okay. So, as temperature increases, the most probable speed, or in other words, the maximum point, decreases. So, shift to the right. Then the curve flattens. So, this is the part that I really want to discuss, distribution of molecular speeds. So, again, we have the most probable speed, the average speed, and the root mean square speed. For the most probable speed, actually, we derive them from integration. Although at the end, the formula really is just square root of 2RT over m. That's for most probable. And don't forget G sub c. We have average speed. This is 8RT over m, and then put pi. So you notice the difference is that for most probable speed, it's 2, no? In the numerator. For average speed, it's 8. But for most probable speed, there's no pi. For average speed, there is pi. Let's compare that with the formula for root mean square speed. If you noticed, most probable speed and root mean square, they both have the same formula, except for most probable, the number is 2. For root mean square, the number is 3. For average speed, it's the only one that has pi in the denominator. And the number in the numerator is 8. So aside from those differences, the formula essentially is the same. No? So it's not hard to memorize. These will not be provided in the exam, most likely. So memorize them. And yes, these will be provided. We have the Gaussian integrals. These are needed if you have this kind of problem. So starting with this function, you have to show that the root mean square speed is equal to square root of 3RT over m. So you have to show the integration. No? So somewhere along the computation, we basically plug and play, and then notice that what you have here matches with the fifth Gaussian integral. Then you just substitute. Then further simplify. Eventually, you have to show that the root mean square speed, URMS, is equal to the square root of 3RT over m. By the way, I have mentioned velocity as v earlier. Right now, I mentioned u. I can't remember the official term anymore, but I think let's just assume that we can interchange how they are pronounced. I don't think it's a big deal anyways. For as long as we are referring to the same idea, then there shouldn't be any point for confusion. Okay? Okay, so this is just basic, no? You have to calculate the three kinds of velocities of the N2 gas in this scenario at a temperature of 25 degrees Celsius. This is in other words to 98.15 Kelvin. We have to convert it to Kelvin. As much as possible, SI units. We use SI units. So, therefore, the universal gas constant is 8.314. Okay? So, just plug and play. And then you get the corresponding answers. What's not provided here is the molar mass of nitrogen. It's assumed that you already know what its molar mass is. So, it is a diatomic element. So, actually, for a single nitrogen atom, it is 14 grams per mole. But since it's diatomic, times 2, so 28. And for SI units, we want this in SI units, we have to convert the gram into kilogram. So technically the molar mass unit for SI unit is kilogram per mole. Okay. Okay, we'll skip this part. Yes. This is important. So the universal gas constant could also be calculated by the Boltzmann constant times the Avogadro's constant. In your calculator, they are assumed as SI unit, as in expressed in SI units. So if you multiply constant, this one being I think 25, Avogadro being 24, you get 8.314 approximately. That is the value of the universal gas constant in SI unit, joule per mole Kelvin. For the molar mass, capital M, or preferably sometimes I write it as double capital M. This is the mass times the Avogadro's constant. So if ever you encounter two of these three values, then you can calculate the other one that's missing. No? And if you express it as universal gas constant divided by molar mass, you rewrite it as this. The Avogadro's constant will cancel, and what you have left is the Boltzmann constant divided by the mass. That relationship can prove really helpful in tricky situations. Maybe the answer to your problem is this one. It's gonna keep you from being stuck. Okay, so these are the relationships between the molecular speeds. And we have the mean relative speed, UREL. We have two formulas now for two scenarios. One is if the molecules are of the same kind. Right? I think an example, generally, one example is the diatomic atoms have no fear of ice cold beer. Hydrogen, nitrogen, fluorine, oxygen, iodine, I think, yeah, called chlorine, beer, bromine, there. So those diatomic elements, those are similar molecules. For two dissimilar molecules of masses m sub A and m sub B, UREL is given by this formula. So just notice their difference, no? Square root of 2 times square root of 8 RT over pi m, m being molar mass. Here, for two dissimilar molecules, you get rid of the square root of 2. What you have is the square root of 8 RT over pi m asterisk. M asterisk, this means this. So, molar mass of molar mass of A times molar mass of B over molar mass of A plus molar mass of B. A and B correspond to the specific molecule. No? A and B are assumed to be different or dissimilar. So, yeah. If you're not given the molar masses, if you're given the masses instead, then use this formula. So instead of 8 RT, it's 8 KT over pi. And then I think this is new, asterisk. Although there's another definition for nu, that's viscosity, but that's for a different topic. It's actually not far from here, but I don't think we're gonna be able to tackle that within this video. So yeah, I'll leave that to you. Let's go to collision frequency. This is gonna be small z because there's another terminology for capital Z later on. So collision frequency, assuming that the molecules are point-like, or in other words point masses having mass but negligible volume, according to the kinetic theory, then this is the formula. Collision frequency is the collision cross-section times UREL times number density. The unit is 1 over second, or in other words, hertz. Collision cross-section, typically this is given, no? For, uh, for gases, you're given its uh, collision cross-section in decimeter. So you'll still have to convert that to meter if you want to express your computation in SI units. So mean relative speed, UREL, we already tackled that earlier. Number density, and also, if ever you're not given the collision cross-section, but instead the diameter, then that is pi d squared. So d is basically collision diameter, or diameter in short. If there are no other underlying contexts, then just assume that d is always going to be diameter. Okay? And for number density, to calculate for this, it's basically P over kBT. So yeah, it's also here. Number density, P over kBT, or N sub A over V. We also have mean free path. Uh, the average distance traveled by the molecules is given by kBT over sigma P. Notice how it's similar to this. kBT, this time in the numerator. Pressure is now at the bottom. And the collision cross frequency is also beside it in the denominator. That constitutes your mean free path formula. So it's not hard to memorize, no? If you see their relationship, you can make your assimilations. So this is the summary of the formulas we've had so far. Okay, so this isn't hard to do. Notice for M asterisk, we use this formula. So we showed it like this. Okay, let's now, oh yeah, it's important you know about this. So what's the difference between repulsive and attractive forces? Repulsive and attractive forces, to begin with, are intermolecular forces. No? In the concept of ideal and real gases, in ideal gases, according to the kinetic molecular theory, we assume that there are no intermolecular forces involved. For real gases, um, since they're real, then there's supposedly intermolecular forces. Two types are repulsive and attractive. No, for repulsive, molecules repel one another. For attractive forces, they attract one another. So yeah, what's the difference between? Never mind. Let's just read from the text. Real gases deviate from ideal behavior due to intermolecular interactions between the molecules. So this is not entirely the reason for real gas deviation, no, from ideal behavior. This is the main reason, rather, though. So for repulsive forces, these are short-range interactions. They are significant only when molecules are in close contact. So yeah, they're expected when the average separation between molecules is small. And yes, they exist at high pressure. Consequently, at the same time though, attractive forces, they exist at low pressure. And they are ineffective when the molecules are far apart from each other. At low pressure, gases occupy a large volume so that the molecules are so far from each other, so that the intermolecular forces play no significant role, and so the gases would behave ideally. Let's look at this illustration. So, our plot is uh, the y-axis is potential energy E sub P, or PE, and we have in our x-axis separation. So notice this region, although it's not really easy to see from the scanning, this is supposedly the repulsion dominant region, this part, where separation is very low. Uh, Eventually, at this region, attraction is dominant. But as we approach a much higher separation, that force of attraction actually becomes weaker until there are no intermolecular forces involved. So, yeah, let's classify this as low separation. Highly positive potential energy, it's greater than zero. Potential energy being equal to zero is somewhere here. So, small separation distance, repulsive forces are dominant. Okay? In intermediate separation, um, the potential energies are negative and the attractive forces are dominant. By the time we reach the large separation region, potential energy approaches zero, as well as the intermolecular interactions. So, this is when the gases start to behave ideally. So, yeah, in other words, it's here. High pressure, repulsive forces. Low pressure, uh, the lowest pressure rather. That's when we see that in large separation. So most likely the gas is ideal. Again, from the kinetic molecular theory, uh, an ideal gas assumes that an ideal gas is characterized by having low pressure and high temperature. So it makes sense now here. For intermediate separation, this is for attractive forces being dominant. This is at pressure being intermediate. So in terms of compressibility, for attractive forces, a real gas is more compressible than the ideal gas. No? Under the influence of dominant repulsive forces, the real gas is less compressible compared to the ideal gas. So mutual repulsion prevents further compression. Compressibility is the ability to put in large amount in a small volume. Okay? So this is the capital Z that I was talking about earlier. Compressibility or compression factor for a while. Mm. Mm. This is what I did not mention earlier, what I could not remember. Virial equation of state. We'll also have this eventually. Um, I'll cut the video here. I'll make another one. Okay? Bye bye.